In this video, which is part 2 of the series on failure theories, uh, I would like to talk about another theory which is called von Mises theory, follow up by the Tresca failure theory that we discussed in the previous video. And this was related to this equation that the maximum shear stress should be less than the shear stress from the uniaxial tension test. And then we got the chart or the graph based on this for different scenarios, if you recall. Now, in Tresca, which is effective and relatively simple, both in theory as well as application, and popularity comes from this relatively simple theory. Only shear stress is considered, but others have looked at this failure criteria, and one of them is von Mises. What von Mises is talking about still applies to ductile material. Mostly these two theories apply to steel type, the isotropic steel type, and similar material. But what happens in von Mises? Von Mises looks at the energy and considers the energy associated with distortion and deformation. Or when a material fails, actually there should be enough energy that deformation happens between the surfaces of the atomic crystal of the material, and that will cause the failure. So we can say that the yielding will occur when the distortional distortional strain energy reaches that of uniaxial tension test. One assumption is that in these two theories is that these material behave the same way under compression and tension. That is related to that linearity that we discussed at the beginning, this linear elastic linear part, as well as hydrostatic pressure, which I will talk about it in this section, doesn't have any effect. So basically, if you do the test under atmospheric pressure, the uniaxial test under atmospheric pressure or under the water, for example, with high hydrostatic pressure, or at least higher than atmosphere, the result would be the same. So this is one of the assumptions that we have. Okay, so what is this? What is this distortional strain energy? So we have to look into that and then take it from there. So we have sigma ij, which is my stress tensor, and eij, which is my strain tensor, stress and strain. Now, what we do here, we come and write sigma ij. If you recall, on the side, I should say that sigma ij is in three-dimensional, is and then symmetry for the other terms. And similarly, eij is, I will not use the matrix, I will use that index notation all the way, but just to refresh memory or see what we are talking about here, I am writing it as matrices. And again, symmetry here. Have this in mind on the side. Now, what we do here, I come here and write this, actually decompose it into two parts. One part is relates to, say, hydrostatic type of stress, and the other part relates to something that relates to deformation or this distortion. We call this deviatoric part, and then we call this, say, volumetric, or sometimes referred to hydrostatic stress. Where actually this should be sigma, where sigma m is the average of the trace. So what we are saying basically here, for this, we come and sum up the diagonal elements and subtract it from the our stress element. The remaining will be the deviatoric stress. If you expand on this, you can see that for sigma ii, the trace of my stress tensor would be obviously this sigma m remains and delta ii plus dii. But delta m by definition is sigma kk divided by 3, and sigma ii is 3, and therefore dii. These two terms are the same. You are basically, these are the trace of my stress tensor. 3 cancels out, and therefore dii is 0. What this means? It means that the deviatoric stress, which is taken away from the diagonal term, maybe I write here for reference also dij as well. Dij is sigma x minus sigma m, only will affect the normal stresses, sigma xy, sigma xz, sigma y minus sigma m, because when you write it, delta I, delta 1 1, delta 2 2, delta 3 3 is 0, and sigma yz, and then sigma z minus sigma m, and symmetry. Only these diagonal terms are affected. So if I subtract the average of my trace of my original stress from each element, then I will get the deviatoric. This is this is all about the operation that I have done here. And if you sum up these diagonals, it will give you 0, obviously, because you subtracted the average, as you see here. This is also true. This is also true for strain tensor, i.e. we can write my Eij as Ekk divided by 3 delta Ij plus epsilon Ij. So this is the deviatoric part, and this is the volumetric part. Basically, this strain, this part of the strain is responsible for changing the size, expanding or contracting a stress element. But this part is responsible for changing the shape. This changes the size. Shall we say? But this changes the shape. And this is this part that we are interested in. So the whole von Monse's failure theory is focusing on these two quantity, dij and epsilon ij. Okay, so what is distortion? Energy. Well, let's call it U, and this is energy per unit volume of your medium is actually 1/2 of sigma ij Eij. This is total energy, right? Because I will get the distortion energy out of this, but if I come and multiply my stress to my stress half of it, and this is very simple to see, in a simple spring, if you have sigma and E, you will see that for linear we get this area. That's what we are talking about. This is the energy or strain energy. Okay. Okay, I use the expression that we had for sigma ij and epsilon ij as we had it. and just simply plug it into this energy equation, and then we work out the multiplication, and this we get these terms. Now, but look at what happens with this term. This piece is actually delta ij replaces the indices. This becomes delta ii. Why is that? Because delta ij is canonical delta, and if I and j are different, it is 0. If it is the same, I equal to j, you get 1. Therefore, dij becomes dii. But this is 0. We already worked it out. But dii is 0 here. So this term goes away, drops out, 0. How about this term? Well, this term is also, if I come here and change color, if you look at this one, this is also epsilon ii, which is 0. We already showed that, did we? No, we didn't. So let's do it quickly. So here we can say that EII is equal to EKK divided by 3 delta II for I equal to J plus epsilon II. But this is 3. Delta II is 1 plus 1 plus 1, because you have to sum up over I index, repeated index, and therefore this one is equal to this one, and therefore epsilon II is 0. This is very similar to what we did for the stresses. So if you come here and get the average of the trace of the strain tensor and subtract it from each diagonal element, then you get the epsilon ij, and the trace is obviously 0. So therefore this will also drop out, 0. So we are left with just 2 terms. But let's look what happened here. Delta ij removes the I and j, so this will be equal to a delta ii. Delta ii is 3, so it will cancel out with the 3, and therefore I will get u, this is total, 1/2 of dij epsilon ij plus 1/2 of sigma m average trace, because this is 3, 3 goes away, EKK. Total strain energy, of course, per unit volume. Okay. The first part, this part, is what we are interested. This is deviatoric part. Let's call it UD. And this is the volumetric strain energy. This is also strain energy, but so this is very important result here. So we are not interested in this because we are saying that hydrostatic pressure, when you have equal uh, stress on all direction for a material, it will not affect your failure. That is one of the fundamental assumption in this theory. So therefore, we have to look at this guy, this first term. So we come here and say, okay, what actually von Mises is saying as yielding will occur when the distortional energy reaches that of uniaxial tension test. Okay, so this is my distortional energy. So let's write it down again. So UD, sorry, don't want that color. UD is 1/2 of dij epsilon ij. Good. Now, for linear elasticity, we have dij, which is the shear strain part, 2g epsilon ij. Remember, epsilon ij is not the total strain, is the distortional or the shear part, because we have already well, it will not affect this, but we have already taken the from total strain, we have taken out the hydrostatic part. Okay, and here G is simply shear modulus of elasticity. Therefore, my UD would be 1/2 dij, and for epsilon ij I use this equation. I use dij divided by 2g would be dij 4g, assuming linear elasticity for stress strain relationship. Now we can expand here, but I will refer you to a reference here at the end for the derivation, and that is calculation of dij. So from here we can say that sigma Vm von Mises is equivalent stress based on your state of stress is square root of 3J2. J2 is the second invariant of Dij. This can be found by calculating the eigenvalues of Dij, this matrix eigenvalues, and writing the characteristic equation, and the coefficient of that characteristic equation will give you the J2. Now, if we write J2 in terms of principal stresses sigma 1, sigma 2, and sigma 3, principal stresses of our strain tensor, we will get sigma v m is square root of sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square, the whole thing divided by 2 and their square root. This should be sigma y. So this is the von Mises equation. If you compare this to the Tresca, you see it's more complicated. Tresca, it was just a simple equation here. Of course, we had to find the tau max, which we did, and we got a shape. But here we have this relationship. So what we do when we have the state of stress, and this is heavily used in finite element method, maybe I mention it here, heavily used in finite element method of analysis. So we get our principal stresses, calculate this relationship, and this should be not more than sigma y. And therefore, if this is the case, then you will see that it is safe. Otherwise, the specimen with or the component will fail. That's what we are saying. You can also write this in terms of just to give you some, maybe I refer you to that before writing too many here. So a reference for calculation of J2 is tensor analysis for engineers, third edition, by myself, MLI, and the year is 2023. To be specific, look at chapter 16. Okay, so if you, I mean, I gave you a formula for not, well, usually we have calculated the principal stresses anyway, but if you want directly go from the original state of stress, sigma x, sigma xy, sigma xz, etc. This I'm referring to this matrix here, shall we say? Then you can also use that for sigma vm. Okay, so having said that, let's look at the 2D plane stress, where we have sigma 3 equal to 0. Okay, so if I come here and write this expression with sigma 3 equal to 0, therefore my sigma Vm von Mises would be, maybe I a little bit zoom in, actually out, and then come back here. So we have this formula. So this becomes sigma 1 square plus sigma 2 square minus 2 sigma 1 sigma 2, and the second bracket sigma 3 is 0, therefore becomes sigma 2 square, and the third bracket sigma 3 is 0, becomes sigma 1 square divided by 2. This will become, we have 2 sigma 2, 2 sigma 1, and 2. So this cancels with 2. So I will get sigma 1 square plus sigma 2 square minus sigma 1 sigma 2. This should be sigma y. So if I square this and divide it by sigma y square and divide by sigma y, I will get sigma y, sigma 1 divided by sigma y square plus sigma 2 divided by sigma y square minus sigma 1 sigma y multiplied by sigma 2 sigma y divided by sigma y equal to 1. So for 2D, if you, sorry, equal to 1, not 0, because I divide by sigma y. So in 2D, von Mises criteria. Okay, so we continue. So what I have done here is basically we got this equation, which is 2D von Mises criteria, and I just graph it here. So if you graph it in a coordinates which is scaled sigma 1 sigma 2 by sigma y, we get a kind of elliptic shape here, but kind of rotated about the axis that goes through 45 degrees at the origin of this coordinate system. So anything that sits inside, if you have a state of stress and sits inside, it it is safe. But if you get a state of stress that in this coordinate system sits outside, according to von Mises, it is failed. It is there's a failure. So this is the safe zone inside this elliptic shape. Now it is interesting that if you draw the Tresca, and I'm kind of scaling it here, Tresca will sit inside this ellipse. And it shows us that if we get a point here or here between the Tresca and von Mises, let me mark these things. This is von Mises criteria, and maybe I use this also here, Tresca, that we had it before, but you can draw it again here or on the top of each other. I'm referring to this Tresca criteria or the graph. And you see here that very clearly that if you are here, according to von Mises, it is safe because inside the elliptic shape. But according to Tresca, it is outside this the, the zone that which is Tresca assumes safe. Therefore, for Tresca is not safe. For example, this point or this point or a point like this. So we can say that we can conclude here that Tresca criteria is more conservative compared to von Mises. This is clearly shown here. Now, uh, it is very hard to draw, but I will show you a picture of it, which is a uh, common license. So this line, which goes through the center, has the direction of unit vector 1 and 1 in this coordinate system. So again, if I come and rotate this vector with the pivot at the origin such that this point, let's call it point P, this point in a sigma y, sigma 2, sigma 3 coordinate system gets the coordinates of 1, 1, 1 in that direction, which is similar to what we had for the Tresca. This vector, we can actually move our elliptic von Mises criteria along that axis and get a 3D. That is called a von Mises cylinder. It's a volumetric, and anything inside that volume is safe, and anything on the surface, it is the limit, and of course outside that surface is not safe. So this is what I'm referring to. This this has common license, so I can use it here uh, with the references that you see. So what we have here, forget about this ring for now. So this is what we are discussing, that elliptic shape and the Tresca inscribed. And then if you expand it along the hydrostatic axis, which is 1, 1, 1 divided by square root of 3, this is this line, the axis. It should be along this axis, and then you get a cylinder. And obviously, similarly, inside that cylinder, you have the Tresca. So this also shows that because any point on this cylinder is basically is the same cross section, means that hydrostatic will not have any effect on your failure criteria. You can question that and say, no, I mean, how about if I do a test under the water and I see a different failure compared to, say, atmospheric pressure, then this cylinder will become a cone, and that is not von Mises yield criteria or failure criteria. That's a different one. So that is something that we have here, and then that will complete the discussion for von Mises. Okay, so I guess this video and the previous video should give you enough background and explanation to understand at least two failure criteria for ductile material. I will follow with some other failure theories for brittle or some extension to the von Mises. And then it is very hard, not very hard, but it is maybe not practical to make an album of all of these criteria. You don't want a menu. Basically, you want the one that you use in mostly in practice, and these two are heavily used in structures and mechanics, Tresca and von Mises. As I said, any finite element package gives you a von Mises plot. Okay, thank you.